Rudolph is famous for having different lives. And one thing, of course, it's very close to quantum computation. So it's not only the philosophy of quantum mechanics which is of interest, but also the applications. He graduated from York University in Toronto, but then moved to Bell Labs, unfortunately not in the middle of last century, when if you were a physicist and wanted to do important things, there was no better place in the world. But now Bell Lab, of course, has become very lousy. And, but still he pursues the work on quantum computing, but now in Silicon Valley and the environment you have there on an extended sabbatical from Imperial. For a while, Peter Knight successfully snatched him to academia, and he spent 10 years in Imperial before becoming a professor there. And he gave a very famous inaugural lecture, which you should look on YouTube, and an introduction where he complained about his cruel parents who prevented from him becoming a pro squash player, which, well, the talk tomorrow is about free choice and quantum mechanics or so. That, I'm not sure if there's some relation, but in any case, when I look at my son, it says something about education, which you should do and you should not do. But then, of course, he's famous for the PPR theorem, which, well, it's the old question about can quantum mechanics be taken seriously? And it's probably the question which has been most often discussed by every physicist. I remember my only encounter with Heisenberg, the other creator of quantum mechanics, when a few students were taken to him there. First question from one of us was, what do you think about the Bohm interpretation? Well, people, of course, and Heisenberg just admitted nonsense Copenhagen interpretation and nothing else. But of course, the questions don't go away. And with John Bell, I talked quite a lot about that, and he was, of course, interested to what extent the Bohm interpretation would be consistent with special relativities or signals don't move far. All these questions, so they exist so on the fringe of philosophy, but also close enough to very practical things like quantum computation. So it's exciting stuff, and so we are happy to listen to it.
Thank you. Yeah, so as you probably gathered from that introduction, I've been a bit scattered in my research life in general, but for the last 2 years I've been working purely on engineering, building a photonic quantum computer and so on. So I haven't thought about foundations, I haven't even given a research talk of any form in 2 years. So you guys are getting the first, the first talk for a while. And I've been sort of madly preparing for this lecture tomorrow night. But when I was asked to give one here, I thought, oh, I'll dig up this paper on the PBR theorem, this talk on the PBR theorem. And while I was going through it, I remembered that when I gave this talk, I got a panicked email so it was at some university, some colloquium, some famous university in the US, where I prepared the talk, and then the person who invited me sent me this panicked email like, we got experimentalists in the audience, don't use too much mathematics or something. And so I had to go through and try and strip out mathematics. I hope you haven't let any experimentalists in here. No, but so the point is that actually I haven't gone and put that math back in. So don't feel it's patronizingly simple. I hope you still get something from it. Okay, I'll come back to this painting, which I own and particularly like, at the end of the talk to explain why I like it so much. Oh yeah, that might be. Let me start by showing you the beach where my parents live. It's 8 kilometers of beach, and they live up the other end because this end is too busy for them. And the one thing I can say about this beach is very exposed, like it doesn't have much shelter, is that the waves on this beach are real, right? Those are waves that you can actually feel, that you can experience in your own life. If you go for a swim, you go surfing. Is there a pointer, by the way, like a stick or something? Should have brought a laser pointer. All right. I'll make do. It'll be fine. And I think so. So those waves are definitely real. And of course, the question in quantum theory is, particularly given the way it was formulated initially, is the quantum wave function real? Okay, that's good. Okay. And it seems funny to even have a question like that in a physical theory these days, but it's not without precedent. I think when Faraday came up with his sort of lines of force, it wasn't clear to people at the time whether these were just a mathematical artifact, something that was useful as a way of thinking about how charges reacted, or whether they were something tangible, like were they a real thing, or were they just something mathematical? And I think it wasn't until we realized that electromagnetic waves are actually built from these field lines that people said, okay, I'm going to really believe that these things are real. Okay. And so the same kind of question is what I'm going to talk about here. Is this thing real? So this is Schrödinger up in the Tyrol. This is his grave. Here's the Schrödinger equation. And I think it's pretty clear from what he wrote was that he had in mind a wave that looked something like this. Okay, he couldn't see that at the time. This here is a diffraction pattern of a single electron diffracting off two copper atoms made at IBM with an STN. And he clearly had that kind of picture in mind, you know, that this psi, the wave function really looked, you know, like water waves. Okay. But the problem that he very quickly realized, well, there were sort of two. One is that it was really built from amplitudes and not probabilities, and once the sort of Born interpretation of the wave function came through, that seemed like a very strange thing. You know, that's not what you would have from a classical wave. But the thing that was, I guess, most troubling was that this state psi was a function over configuration space. It's not a wave in the real world unless you only have one particle. Okay. And so what I'm going to talk about in here is a sort of question that it seems crazy that we have this theory that's so old and yet we're still asking this question, which is, what is the status of psi? Okay. And the distinction that I'm going to talk about is the status between what we call psi is ontic or psi is epistemic. Okay. And let me try and sort of define that for you. But I'm going to start by giving you definitions for something that we won't argue about, which is for a classical object. So I'm going to talk about flipping a coin. Let's talk about the distinction between ontic and epistemic. Okay. So this is just a schematic of all the possible real states of the coin. So real states here are going to mean the real physical states of the object. And so for a coin, there's many different physical properties that go into making up the real state. There's its mass, its height, its speed. Okay, and one of those properties might be, oh, this coin is showing heads upwards. Okay, but there's a whole bunch of things that go into making up the real state, the sort of list of all the properties. And of course, in physics, you don't need. So some of those properties can be derived from other ones. And in physics, you know, you could probably recover 90% of modern physics if you just understood the actual geometry of the real states of the coin under some sort of notion of two real states that are close have physical properties that are close. But what I'm going to talk about, I'm not going to care at all about like the geometry of the real states, kind of what type of mathematical object they are. Okay. There's going to be some type of mathematical object that captures all the physical properties of the coin. Okay. And so when we flip the coin, you start with some value. The coin starts here at a certain height, at a certain location, with a certain velocity, and so on. And then as it evolves, as I flip it, it just sort of evolves through the real states of the coin. So maybe it's here in the air, and then it lands here. Okay. And so, if you, another example would be a particle in phase space. So typically in classical physics, the set of all real states is just the phase space of the system, right? And motion, like dynamics, is just a motion through the phase space. Okay, and so what does it mean with a coin flip, we normally want to break the real states up into those that correspond to heads and those that correspond to tails. Okay? And what it means when you say, like, oh, it's an unbiased coin, you mean to say that the set of real states that you say that are consistent with your knowledge of the coin, okay, assuming that you don't sort of favor some over the others, so let's just take a simple case where you sort of uniformly assign to the real states. Well, then you have, as half the area of these real states lies in the region of heads and half lies in the region of tails. Okay. There's of course plenty of real states, possible real states of the coin, like the coin is on the moon or something, that you assign probability 0. Okay. And so this is what you have sort of implicitly going on in your head when you assign the coin something that I think we would all agree was an epistemic state, the state of our knowledge, which is, we say, the probability of the coin being heads is a half. Okay. Feel free to stop me if you want to argue, by the way. You should never say that in a foundations talk, but it's fine. Okay. So here would be, say, a different case. Maybe I flip the coin in a way that you assign there being, 2/3 probability of heads and a 1/3 probability of tails. And so possibly this different way of flipping the coin, this is the set of real states that you say are consistent with your knowledge of how I flip the coin. Okay. And the thing that's going to be important to us here is that it's quite possible to have an overlap region. It's quite possible for me to prepare the coin in those two different ways, the one in which you assign there being a greater probability of heads and the one where you say it's unbiased. But it's quite possible for there to be real states of the coin, values of its position and velocity and so on, which are consistent with both of these states. Okay. So these states, these epistemic states, it's quite possible to have the real state, or what we call the ontic state, consistent with more than one epistemic state. Okay. And so that's this overlap region that's going to be sort of critical to what we're thinking about, because we're now going to ask a sort of question for quantum theory, which says, regardless of what you believe the real states of the world are, okay, I'm going to think about just some completely abstract space. There really needs to be no structure in the space other than the fact that it's a measure space so that I can even talk about probabilities. But other than that, there's some space of real states of the world. Maybe you think that space are the quantum states. Maybe you're a Bohmian and you think it's the quantum state with some other variables added, whatever it is that you think. The question we're going to try and ask is, do those real states, do those real states overlap? Are there do the epistemic states that correspond to psi, like this, overlap? Or are they kind of disjoint, like this? That's the basic question. So for the same, and this is from a famous physicist. I'll explain where the sentence comes from in a minute. But what we're saying is, for the same ontic/real state of a system, in this case, what he called B, are there two or more equally justified quantum states? So when I prepare a quantum state of a system, can it ever be the case that I prepare two completely different quantum states, but the system, a bit like the coin, has a real state that's in common to the two quantum states? Okay. So this is just a distinction in how you might map your understanding of what the wave function is, depending on what your particular biases are, at some point, if you're going to do physics and do mathematics, you have to commit yourself to what real states are consistent with a particular wave function. And then we're just asking a purely mathematical question: are there any real states that are in common to one or more of those quantum states? Okay. So, yeah, we basically want to decide this and this. The notation we normally use is that we label a space of real states capital lambda and a particular real state little lambda. Okay. Now, I guess one thing that can take a little bit of justification is why might you even think that this was the case? You know, there's plenty of people out there who say no, the quantum state psi is the only real state. Okay, in which case they're basically thinking something like this, but where there's just a single lambda for every psi. And so here's some arguments that over the years people have put forward as to why psi is epistemic, why there's some overlap in the real states corresponding to different state psi. So one of the arguments goes like this: take a source of light, filter it down to a single photon, so maybe this is some polarized sunglasses, I have a horizontally polarized photon. And when I prepare the photon horizontally polarized, and when I prepare it 45-degree polarized, so over here I'm doing something that's macroscopically distinguishable. These are definitely different preparation procedures. But when I get down to the level of the single photon, and I have these two quantum states, there is no measurement that I can do which will tell me which of these two preparations was actually the case. Okay, these two states are not orthogonal, so there is no way of fundamentally telling which of the two macroscopically distinct ways were used to prepare it. Okay? And so an argument for psi being epistemic is that fundamental indistinguishability is easy to understand because the horizontally polarized photon corresponds to this red region of real states, whatever they are, and the 45-degree polarized photon corresponds to this green one. And sometimes the real state of the photon, whatever the heck it is consistent with both preparation procedures. And so therefore, you shouldn't expect there to be a way of unambiguously determining which of these two states the system was actually prepared in. Okay. So that's sort of one argument. The second argument, I think the most compelling one to me in this kind of story is collapse, right? Like if you take classical probability distributions and you, by one means or another, gain some information about a system, then you instantaneously change the probability distribution. It's not a mysterious thing. But collapse of the wave function does seem to be mysterious if you want to take the quantum state itself as being real. Okay. And so here's a quote by Bill Unruh, who sort of follows this view that psi is epistemic. The wave function is not a thing which lives in the world, it's a tool used by the theory to make inferences from the known to the unknown. Once one knows more, the wave function changes, since it's only there to reflect within the theory the knowledge one assumes one has about the world. Okay, so I find collapse the most compelling argument, I guess. There's a few arguments that are more sort of quantum information-y. So if I give you n different coins, I can only send you n bits of information. But to specify a probability distribution over n coins, it takes 2 to the n real parameters, because I have to say, here's the probability of heads, 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 here's the probability of heads, 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 tails, and so on. Similarly with the quantum state, if I give you n spin half particles, I can only send you n bits of information. Okay. And yet it takes 2 to the n complex parameters to specify the quantum state of n particles. So there's this big exponential gap between the sort of your description and how much information you can transmit. Okay. And you know, here, the 2 to the n parameters, it was clear that that was just you ascribing probabilities. That wasn't the real state of the thing. That's just what your knowledge of the coins were. And so maybe it's the same for the quantum state. Okay. There's a whole bunch of other things, and people have, you know, found many analogues between, I would call them analogues, between classical epistemic states, which are probability distributions, and quantum states. The classical epistemic states cannot be cloned, much like quantum states cannot be cloned. They can be teleported, much like quantum states can be teleported, and so on. Okay. The other argument for why you should think that psi is epistemic is that all the psiontic interpretations we have are kind of weird, right? They're things like Bohmian mechanics. You have a high degree of non-locality. They're things like many worlds interpretation, and so on. Okay. So you might just say, well, no one's found a psiontic interpretation, where they take that the wave function is all and everything there is, that's very compelling to the whole physics community. And so maybe we should assume psi isn't a real state. Okay. So let me just run you through an argument that Einstein gave that this must be the case, that when you have two quantum states prepared something like this, that there must be some real state that's common to two completely different quantum states. Okay. So Einstein's argument went like this. It's a steering argument. He said, consider a pair of entangled systems. Okay, in this case, I'm going to write things in terms of spin half particles, so up and down, or spin up and down in the z direction. And the first particle is held by A, and the second particle is held by B. Okay. And A and B are far separated from each other. And now A does a measurement, takes a Stern-Gerlach device, and does a measurement of the z component of the spin. Well then, some of the time, A collapses the spin that B holds to being spin up. Okay. Similarly, if A takes a Stern-Gerlach device and orients it in the x direction, then A collapses B to having a particle with spin that's up in the x direction, so x-directed spin. Okay. And this quantum state is completely different to this quantum state. And what Einstein said is, look, the real state of B is unchanged. A is arbitrarily far away. The real state, lambda, whatever it is, I'm non-committal as to what it is, but there's more than one quantum state associated with lambda. Okay. This was the argument he gave. Unfortunately, he never published it in a paper. It's only given in this letter to Schrödinger from 1935. He just says, the real state of B thus cannot depend upon the kind of measurement I carry out on A, separation hypothesis from above. But then for the same state of B, there are two, in brackets, in general, arbitrarily many, equally justified psi B, which contradicts the hypothesis of a one-to-one or complete description of the real states. Okay. And I think that argument, if Einstein had been more vociferous about it, I think at some point he just gave up. That argument should have been the argument of the EPR paper, and I don't think there really is a good counter argument to that. Okay. But of course, he's assuming locality. And so I don't think until Bell came along, there was really a good argument against this. Okay. So what I'm going to talk about is a result which surprised and bothered me, still does, that shows that, contra what Einstein said, in reasonable physical theories, it must be the case that the real states associated with different quantum states are completely disjoint, like this, that there's no overlap. Okay. So we kind of know that Einstein's argument was dodgy because of Bell, but I'm going to try and get to show that this is the case, and I'm not going to sort of follow something like Bell. Bell doesn't let you conclude this per se. But notice that if this is the case, then the world has to be highly non-local because of Einstein's argument, which says take an entangled state and steer the quantum state of a remote system. Then if that's what's happening, then as I steer to these different quantum states, the real state of the world, whatever the heck it is, must be moving around of the remote system. And that's a fairly extreme version of non-locality. Okay, yeah.
The distinction between what you just said about Einstein's argument and what's in the EPR paper, can you make that a little?
So the EPR paper, so it's really worth reading this letter from Einstein to Schrödinger. Like he basically, this is after the EPR paper, and so Einstein never saw the EPR paper. He went to IAS, he had some discussions with Podolsky. Podolsky wrote it up and submitted it without Einstein ever seeing the paper. And the problem with the EPR paper, I mean, there's sort of multiple ways of seeing problems, is that it confuses, like Einstein was here just talking about, is there a one-to-one relationship between real states and quantum states? Okay. And in the EPR paper, it becomes mixed up with the uncertainty principle, right? Like it's sort of sounds like trying to get around the uncertainty principle. And then the degrees of freedom that are used in the EPR paper are actually bad degrees of freedom to use when you want to talk about sort of physical properties of separated systems, because it's relative position. Relative position does change when you do something here. And Bohr's response was basically to just sort of build a device that does relative position measurements and show that the uncertainty principle was fine. It has completely got nothing to do with the actual argument Einstein was making. Right? In the letter, Einstein doesn't even say what type of physical system. He just says, look, I can make an entangled state, and I can collapse to different quantum states arbitrarily far away.
If I took the entangled pair and then EPR's assumptions of separability and realism, you would come to the conclusion that it's incomplete, which is roughly the statement, right? That for every real state there can't be a corresponding quantum state, so quantum mechanics is incomplete. So they're very close.
Okay. Let's not get too far down this rabbit hole. But let me tell you why I know for a fact that they're not close, which is that there is a local hidden variable model for the EPR argument, but there is no local hidden variable model in general, and this is what this kind of thing proves for you. So if I take Gaussian states, EPR state is a maximally entangled Gaussian state. Position and momentum measurements are just Gaussian measurements in phase space. I can reconstruct the whole EPR argument, and I don't need anything to do with non-locality and so on. I mean, Bell realized that, right? He sort of says it in this thing. So I don't think the EPR argument can really capture this fundamental distinction. But yeah, I think it's really just, it's sort of an unfortunate fact of history that was the particular argument of Einstein's that somehow got through this Podolsky.
So Bohm's update of EPR's argument is kind of what was already in Einstein's letter.
Yeah, basically. Except Einstein was very clear about it. Like, it was just literally, there's a real state, I collapse to different quantum states. Look here. Okay, so I'm going to now run you through this argument which says that this must be the case, and that's done by a different kind of method. It doesn't use sort of entangled states of systems and so on. But in order to understand the argument, it helps to think about a classical problem first. Okay? And so the classical problem that I'm going to think about involves just a die, or a dice. A die. I don't know, is die the plural or dice the plural? Dice is the plural. Okay. So I have one die, and the real state of the die is just the number that's facing upwards. Okay. And I'm going to consider two different states that classically are unambiguously epistemic. So they're going to be the classical epistemic state where, however, because you know something about how the die was prepared, you know that the number showing upwards is even. So rho E means even, which means that you assign a probability 1/3 to 2, 4, and 6. But there's a completely different preparation which could be done on the die, which called rho prime, where you assign a 1/3 probability to 2, 3, and 5, because those are the prime number preparations of the die. And we're going to think completely operationally. You don't really need to know anything about what goes in this box, but someone can press a button here. And if they press the P button, then the die is prepared with a prime number showing upwards with equal likelihood, and if they press the E button, then the die is prepared with an even number showing upwards with equal likelihood. Okay. And now, imagine we have two such preparation devices. We build them, they're independent, and they're operated independently. And someone comes along, maybe you're a beginning grad student in some lab somewhere, and says, I want you to build me a measurement device which can take in the two die. Okay, here the lambda, the number showing upwards on the die. Take in the two dice. I've been speaking American for too long. I've forgotten how to speak English properly. So this measurement device only gets to see the two dice coming in. And then it has to obey the following rules. The measurement device has to give one of four possible outcomes. You can see the labeling of those outcomes here. And they have a kind of weird negativity about them. When the outcome is not PE, then you can only get this outcome for the three cases which do not involve P being pressed on the left and E being pressed on the right. Okay. So for example, EE, it's possible to get the not PE outcome. And PP, it's possible to get the not PE outcome, and so on. But you cannot get this outcome if you do press P on this side and E on this side. Slightly weird type of measurement. Okay. And similarly for the four outcomes. So you have to give one of these outcomes, and essentially this is just a measurement that rules out one of the four possible combinations of preparations. Okay. And the question is, if you're a grad student and someone says, go to me the lab and build me this, I've got a big grant to go and build this dice measuring device, are you going to be able to succeed? It's a question for the audience.
How much money do you get?
Yeah. You know, graduate student stipends are so great these days. You don't need money.
I've seen the answer, so I can't.
You can't say it, yeah. Okay, so let's imagine that you're really trying to build this device. So you say, okay, what am I going to do? I'm going to program this device, so the dice comes in. What am I going to do if, for example, a 4 shows on dice 1 and a 5 shows on dice 2? Okay. Well, if I see a 4 on dice 1, I know for sure that this was prepared by pressing the E button, okay, because 4 is even. And if I see a 5 on dice 2, I know for sure that this was pressed by pressing the P button. Okay. So in that case, I know that E was pressed here and P was pressed here. So I could, for example, program the device to just give me the not EE outcome. Okay, because it's not the case that E and E were pressed. Okay. So what do I do? Can anyone see how this becomes problematic? Okay. Let's go back and look at these two epistemic states. Okay. The number 2 is problematic here because it's a real state that is consistent with both epistemic states. Okay. But what happens, for example, let's say you've got 2 here and, 6 here. Even then you would be okay, because you would know, if you see 6 over here, then you know that the E button was pressed over here. So you can give an outcome like not EP or not PP. Okay. So the only time that you're really in trouble is when you see a 2 on both of these die, because then you don't know enough about the preparations, And if you had if you were a grad student, you had a supervisor like mine, it wouldn't have been a question of getting money. It's like, I'm going to kick you out of grad school if this thing doesn't work. And, she was really mean to me. So you would not want to take the risk. Okay? This measurement device has to work 100% of the time. Okay. So hopefully you see that it doesn't really matter kind of what we're talking about. It doesn't have to be DIAS here or anything. If it's the case that there is, the only information a measurement device has comes to it via the systems. If it's the case that there are real states of the system which are ambiguous, they lie in an overlap region of the two preparations, then some of the time, in this case 1/9 of the time, but some of the time, the measurement device cannot work. Okay. All right. And so here's just stating that this is impossible because the same ontic state, lambda, corresponds to two different epistemic states. Okay. So now let's talk about the quantum state preparation. I've got the same box here. Of course, the internals of this box are different. But basically, when I press a P, instead of meaning prime, it's just going to mean I prepare to spin up in the Z direction. Okay. And when I press, and so you can sort of think of that as, I just have inside here some Stern-Gerlach device that filters the thing when I press P, and so this comes out. And when I press E, I get spin up in the X direction, which is a non-orthogonal state to spin up in the Z direction. Okay? But at the end of the day, out comes the system, whatever spin particle it is, or it could be a polarized photon, doesn't matter. Okay. And the fundamental question we're trying to answer, remember, we want to be completely non-committal as to what the real states of a system are. We're just trying to say, is it the case that the same ontic state, lambda, is ever prepared when different buttons are pushed? Okay, is there an ontic state that lies in some sort of overlap region of these two possible quantum states? Is there the equivalent of the number 2 for the quantum state? Okay. And so the surprising thing, at least it was to me, is that in the case of preparing quantum systems with non-orthogonal quantum states, so there's still 4 possible preparations, up in Z, up in Z, up in X, and so on. There's these 4 possible preparations, but now it is possible to build this measurement device. Okay. There exists a way of doing it. I found this particular one on MATLAB, so I wouldn't say it's particularly intuitive, but I'll show you how it works. You build this measurement device to project onto these 4 orthogonal states. Now, it's not obvious that these are 4 orthogonal states. This is up, down in Z, down, up in Z. It's an entangled state. But this is like up in Z, down in X, and down in Z, up in X, and so on. But if you do the algebra, you can check that these are actually orthogonal states. Okay. And so you build the device, however you build it, some sort of interactions, such that it does the projective measurement onto these 4 basis elements. And now let's compute what happens when you put in up and up. So when this box presses, the P is pressed, and on this box the P is pressed. So when you get a P and a P, okay, then you've prepared up and Z on both of the particles. But up and Z is orthogonal to the first measurement outcome here. So you can program the device, you can associate this outcome with not PP. There's some probability of getting the other 3 outcomes. But you can say this measurement outcome, whenever you see this, point to the not PP, because it will definitely not be the case that P and P were pressed. Okay. Similarly, if you press P on the left box and E on the right box, then you have this product state, up in Z, up in X. And this has 0 overlap with the second measurement basis outcome. And so you can associate this outcome with not PE. Okay, and you can guess where it goes. The other 2 preparations each have overlap 0 with the other 2 measurement bases. And so you can assign outcomes to the 4 measurement outcomes that obey the rules of the box. Okay. And so that tells you that lambda must correspond uniquely to a quantum state psi. There's no equivalent of the number 2. There's no real state that's in some overlap region. Okay. Now, yeah, so we're kind of in this situation here. So, what can you conclude from this? I think what I would say is that we can conclude that quantum states are not naively epistemic, that we need some other notion of epistemic. If you want to hold to the idea that quantum states are epistemic, that are just to do with our knowledge of the world, we need some other way of talking about them. Let me just emphasize, though, that there's sort of 2 assumptions that are going into this. The first is the assumption of realism at all, right? You can just say, I'm going to throw out realism for microscopic systems. Maybe I think it would be hard to be a physicist and not embrace realism for macroscopic systems, but you could certainly imagine saying there's some sort of failure of reductionism in our thinking like that, and so we just throw realism out completely. The other assumption that I'm making here is really that I can build 2 copies of a box and operate them completely independently. Okay, and I don't have entangled states here. But I do have entangled measurements. So I really need that these states are not entangled, that they're just product states. And you could say, well, maybe there's some sort of conspiratorial thing that sort of correlates the real states in these systems. And people have looked at models like that in order to circumvent this result. They tend to be pretty unnatural, but my sort of counter-argument to that is along the lines of, how would you do science if you really believed in such a conspiracy? Science is built upon the notion that I can do an independent verification of one experiment here, and if I can't go and build an independent copy of the same experiment over there, then I should go back to the beginning and say, why do I believe what I believe about the world at all? Okay. All right, so just to compare it to Bell's theorem, so Bell starts with quantum theory and realism and free will, because he has to say there's no superdeterminism, and gets non-locality by looking at measurements on entangled states. Here we also are assuming quantum theory and realism, and the equivalent of the free will is this preparation independence. There's no sort of hidden correlations between supposedly independent devices. From that we include that the state psi is ontic, i.e. there's disjoint regions of space associated with different psi. And so from that, because you can apply Einstein's argument, which says, well, you can change psi remotely. If I can change psi remotely and I'm in the psi-ontic theory, then I'm changing the real state remotely, so I also get non-locality. Okay. Now, I just want to finish with sort of saying, so when this result came out, many people who advocate a Bohmian point of view or many worlds point of view said, oh, you've just completely killed all epistemic approaches to quantum theory, okay? Which bothered me because, I've spent most of my career, advocating one way or the other for some kind of epistemic approach to quantum theory. So I think it's useful to be clear about which particular type of epistemic program is getting ruled out. So program A in the sort of epistemic programs of quantum theory is the one I would have said is the most natural and nice. It's the one that you might advocate in analogy with thermodynamics. You say, well, I'm going to start with just standard logic. I'm going to use standard classical probability theory. I'm going to assume that a measurement is some sort of response to some real state of the system, and that quantum states correspond to ignorance of the real states. Okay, so sort of like the simplest, most naive type of hidden variable theory. And then in this sort of program, I say, well, the physics is in the real states, whatever they are. and we should spend our life trying to work out what they are and how they act, and we know they have to be non-local because of Bell and so on, but that's where the interesting physics is. And it's this that essentially has been ruled out by this result. But there are other programs, and I think it's worth understanding where they fit in our thinking. So the second program is one where you say, I'm going to take standard logic and standard probability theory for classical observed data, but I'm going to deny that measurements are responses to real states of the world. Okay? That when we do a measurement on a system, I'm going to say that is not due to there was actually a system there with physical properties like mass and charge and spin and so on, and the measurement reflects the values of those properties. Okay. So under program B, what you see quantum states are, they're objects for just quantifying and assisting us doing inference when we've sort of denied reductionism for realism. Okay. And in this program, what you find is that the quantum inferences become like a special shape of a subset of the classical probability theory. Okay. And you say that understanding quantum physics is about understanding this subset of the space. And this is the view that's most clearly advocated by Chris Fuchs. Okay. And so if you're interested in this view, this is where to go. But because it doesn't have a lambda, because it like very explicitly denies the existence of real states and ontic states, then this is not ruled out by these types of thinking. It also, let's not get it too deep into that. There's a third program which I think is still, it's a lot more nascent, which is to say that we're not really using classical logic and classical probability theory. We're using some new non-commutative rules of logical inference and probability theory. And so quantum states should be sort of understood as a completely new type of inferential object. It's built around this non-commutative probability theory. There are some things missing from this, like what is the conditional density matrix and so on. It's difficult to construct conditional density matrices that work in all situations. But you sort of see now, in this view, you throw out the kind of classical probability distributions, except that somehow at the end of the day, you've got to get them out of the very final measurement. Okay? But you say that quantum states are some non-commutative generalization of classical probability theory. And then people like me say, well, where's the physics? Where am I going to find the physics? And the people who advocate these types of view normally the physics is in something to do with the causal structure of the world. Okay. If you want to read, I think, a really good essay on this, it was a prize-winning essay on this type of view, Rob Speckens has a nice article, The Paradigm of Kinematics and Dynamics Must Yield to Causal Structure. Okay, so programs B and C, I think, are still tenable. I don't particularly like either of them. Okay. And the reason I don't like either of them, I think, is summed up in this painting here. So this is a painting I bought from the artist Geraldine Cox, who was trained as a physicist and does a lot of physics type of paintings. And it's just from an old photograph of two physicists looking at the spectral lines on a photographic plate. Okay? And you can't really see it in this picture, but the spectral lines kind of almost float up off the image. And all the human-based stuff in the background is just sort of blurred and indistinct. And these are very sharp. And these lines are caused, by light that was emitted from a star long before humans were around. Right? If I take quantum theory at face value, the state of the atom that emitted that light in those stars, billions of years ago, changed when we made that observation. Right? I find this very implausible, but I also think that whatever my interpretation of quantum mechanics is, it really has to tell me, why is it that I have the Hamiltonians I do? Why is it that the lines lie where they do? And I totally believe that all of this stuff here that would be there whether or not we had actually evolved. And right now I don't see any route through the various epistemic programs to making me comfortable with how it is that quantum theory, I think, should still go on and be relevant even in a universe without us. Okay, so that's the sort of summary of the conclusions. None of them are very appealing to me. It's sort of giving a talk with conclusions that all the conclusions I think are pretty ugly. Okay, not the speaker, but the conclusions are all pretty ugly. The quantum state is real. That sends you down a many worlds or Bohmian view. It's not possible to do independent experiments. That makes me think, how do we do science at all? Or that I have to deny realism somewhere, and then I have to answer the question, where and why does that denial happen? So I'll leave it at that. Thank you.
Questions? Well, then let me ask the question. Of course, one of the reasons for the talk here, and definitely reason for the talk tomorrow, is the 75th anniversary of What is Life. Mm-hmm. Now, at that time, Schrödinger thought, wrongly, as we seem to know, that quantum mechanics had to do something with the possibility of life. But at the end of his lectures, he asked if quantum mechanics has to do something with consciousness. Mm. And this is a question which just doesn't go away, though people would argue that it makes no sense or whatsoever. So what is your view on that?
I think the quantum mechanics having something to sort of do with consciousness, other than the sort of trivial fact that chemistry depends on quantum mechanics, I am very skeptical about, although I'm certainly no expert on it. But I think, and this is, I think it's very easy to understand why Schrödinger was thinking about these things. So when that letter from Einstein came to him in 1935, he then generalized the calculation that Einstein had done. So in the letter Einstein does a little calculation. And that was what led to these two papers in 35, which the one that has the Schrödinger-Cat paradox in it, and the other one that sort of looks at the full probability distributions that you can create by separated systems. In fact, he speculated in that paper something like dephasing might prevent these kinds of things happening. But it's clear that at that time, and I think even now, it's natural to ask the question of how much are our physical theories caught up in the fact that we are conscious beings, that we are doing, we've got these fat fingers that don't let us push on the world without affecting it. And so if you say, look, the way that our physical theories are constructed, it's like, we're like bulls in china shops. They're just we're smashing stuff all over the place, and we're trying to make inferences about what was going on before the china smash. And then we're trying to ask questions like, what would have happened if I hadn't have walked into the shop and smashed the china, and so on. You can see that it's very tricky, and that's the kind of thing Schrödinger was thinking about. So I think that he sort of rightly saw this fact that there's a real tension between thinking of quantum theory as a thing that goes on and happens independent of us, and that it's the correct description of the world independent of conscious beings, and the reality, which is that when we do measurements we disturb things and so on. And the thermodynamics, classical thermodynamics, I think is similar in some ways, right? Classical thermodynamics is about the stuff that's relevant to us. It's not relevant to those particles. Entropy is a purely epistemic concept. So we have examples of theories which are very anthropocentric, and I think he was rightly aware, of how anthropocentric that kind of thing is, and we probably won't make progress on understanding quantum theory until we can get rid of ourselves and get rid of the conscious, all the things that we as conscious beings do. But the flip side of saying, oh, well, then just because I've got a mystery of quantum theory, that then, underpins another mystery of consciousness that just seems like conflating mysteries and hoping that, something works out of it. I think I'm much more skeptical of that. Yeah.
Yeah, I share your skepticism about many world interpretations, but there are people who sort of religiously almost believe in it and say it's
Yeah.
just, the quantum state is everything and nothing else happens, it never collapses.
Yeah.
Is there anything actually logically wrong? I mean, it seems to me a horrible proliferation of possibilities, but
Yeah.
logically you can't rule it out.
So logically you can't rule it out, but so in fact the thing I was talking about before I think is possibly useful, which is if you take the Gaussian subset of quantum theory, i.e. all the Gaussian states, so that has lots of entangled states, position, momentum, measurements, all this kind of stuff. So that has a very natural formulation in Hilbert space. And in that theory, you have the measurement problem. You also couple, that in fact, if you look at von Neumann's original description of the measurement problem, well, the problem was all in terms of Gaussian states. He had a pointer, he had some spreads of position momentums, and he displaced it and so on. So that theory, formulated in Hilbert space, seems to require many worlds or something, something strange about it. But then, if you take just that sub-theory of quantum theory and do it in the Wigner distribution picture, it's all local, it all makes sense, there's no many worlds, there's no, weird, dodgy stuff that has to happen. So, my gut feeling about things like many worlds, and the interesting thing to say is, although there is that local Wigner distribution way of interpreting Gaussian states, the Bohmian view of it is still non-local. And I think that this just tells me I should be skeptical of interpretations that are based on kind of Hilbert space pictures of the world. But, obviously we don't have hidden variables along the lines of Wigner distributions, and these kinds of things tell us that if we try to, they're going to be weird and so on. So it's, it's more a gut feeling than anything. Yeah.
In the path integral interpretation, the wave function takes a step into the background.
Yeah.
And these questions they seem to me they look quite different.
Yeah.
Do you have anything to say on that?
So I've tried a few times in my life to kind of come up with a realist view of the world based on taking paths and path integral, like taking the paths in some sense as the ontic states. It's mathematically a bit messy, and path integrals are, go and look at how many times Feynman mentioned, does a path integral with two particles, right? Almost no one ever really does it, right? We either use them in a very abstract way as essentially a way of avoiding putting a proper measure on a space and sort of mapping a theorem. Yeah, so what
they take the step back into the collapse of the wave function.
Yeah.
Is less obviously necessary there.
It's definitely less obviously necessary. So I think it's certainly a plausible. I'm a committed realist in the sense I think there is something out there and something going on. So I would like to take path integral interpretation and say I'm going to identify something within this as being what's really going on in the world. I know it has to be non-local, but whatever, I'm going to take it. But the real problem is when you start trying to describe entanglement in a path integral formulation, it's very messy. How do you do that, the Bohm version of the Bell experiment, of the EPR experiment with path integrals, right? It's just a mess. So, yeah. But, we know it has to be weird no matter what. So I think, I certainly don't rule it out as an option. I think it just needs someone smarter than me to try.
Suppose that either your group or Station Q people also built a functional quantum computer. Would you have some kind of experiment in mind which you could do to pursue these questions in a bit deeper way?
I think there's certainly questions you can have about, like, is there fundamental decoherence? Because I'm fairly skeptical of that, I'm not building a quantum computer to try and answer that question. But there are people, so for example, collapse theory models. Most of those models do not, so I'm trying to build a quantum computer from photons, and collapse theories, they studiously avoid light because it basically doesn't decohere. So, but yeah, I think someone building a quantum computer from, let's say, matter-based qubits could say that they've really, or it seems very likely to me anyway, that they would rule out large parameter spaces for collapse models. But with photons, yeah, like collapse models tend to avoid the photons. Yeah.
Okay. Thanks a lot. Yeah.